We want to now look at the concept of independence when we're looking at jointly distributed random variables. Now, two discrete random variables, x and y, are independent if and only if the following equivalent conditions hold for all x and y. So the first is that the joint PMF is the product of the marginal PMFs. Again, this has to hold true for all values of x and y. Second is that the conditional PMFs are the same as unconditional PMFs. So this is the conditional PMF of x given y. That's just equal to the marginal PMF of x. This is the conditional PMF of y given x is equal to the value small x. And this is equal to the marginal PMF of y. So now, since all these conditions imply one another, so proving any one condition is enough. So if you want to show that two discrete random variables are independent, you don't need to prove all three of these. You can just prove any one of these because all of these are equivalent. They all imply one another. So if you prove one, it automatically implies the other two. Now, proving one condition is enough to show the independent, but you need to prove it for all x and y. So you need to prove it for every possible value of x and y that your discrete random variable takes. What do we mean by this? If we go back to an example that we were looking at, so I would have to show, say I wanted to show the joint PMF is equal to the product of their marginal PMFs, right? Okay, probability x is x and y is probability x is equal to x into probability y is y. I would have to do it for every possible x and y. I would first need to do it for this ordered pair, x is 0, y is 1. I would need to show that probability x is 0 and y is 1 is probability x is equal to 0 into probability y is 1. We would then need to do it for this ordered pair as well. We would need to show for 0, 2 that probability x is 0 and y is 2 is probability x is equal to 0 into probability y is equal to 2. Similarly, we would need to do it for this ordered pair 1, 1. We would need to do it for this ordered pair 1, 2. If we wanted to show the conditional PMF of x is equal to the given y is equal to the marginal PMF of x, right? We would again need to do it for every x and y. We would first need to say do it for first we would, like, for example, look at the conditional PMF of x given y is 1, and you would show probability x is 0 given y is 1 is probability x is 0. Probability x is 1 given y is 1 is probability x is 1. So we would need to show the conditional PMF of x given y is 1 is equal to the marginal PMF of x. Similarly, we would need to show the conditional PMF of x given y is 2 is equal to the marginal PMF of x, right? So it's like we would need to show, okay, probability x is 0 given y is 2 is probability x is equal to 0. Probability x is 1 given y is equal to 2 is probability x is 1. So we can prove similarly, we could do it for the conditional PMF of y given each value of x. Like we would have to look at the conditional PMF of y given x is 0. We would have to look at the conditional PMF of y given x is 1. So essentially the idea over here is this, that because these conditions imply one another, if to show they're independent, you can show any one of these conditions holds for all possible values of x and y. Right? You don't need to prove all three of these. You can prove any one of these, but you need to make sure you prove it for all x and y in order to claim they're independent. If we can show any one condition is not true for a single pair x and y, we have shown x and y are not independent. So if you can disprove by just one case, so if you're able to show that any one condition is not true for even a single pair x and y, so we have shown they're not independent. But to prove independence, you need to prove any one of these conditions for all possible pairs x and y. So going back to that same example, if I can show that probability x is equal to 0 and y is 1 is not equal to probability x is equal to 0 times probability y is 1, I have shown they're not independent, I can conclude they're not independent. But if I end up getting that probability x is equal to 0 and y is 1 is equal to probability x is equal to 0 times probability y is equal to 1, then I cannot conclude they're independent by just this one case. I will need to see if the joint probability is equal to the product of the marginal PMFs for every possible ordered pair xy. I would need to prove it for x is 0 and y is 1, for x is equal to 0 and y is 2, for x is 1 and y is 1, for x is 1 and y is 2. So if I can, if I do end up getting that if I don't end up getting that probability x is 0 and y is 1, it's not equal to probability x is equal to 0 times probability y is equal to 1, then that's enough for us to conclude they're not independent. To show they're not independent, you just need to show any one condition does not hold for any possible pair x and y. But to show they're independent, you need to show the condition is true for every possible x and y. Similarly, if I end up getting that probability x is equal to 0 given y is 1 is not equal to probability x is equal to 0, that's enough to conclude that they're not independent, right? Because to prove they're not independent, you just need to show that any one condition is not true for a single pair of x and y. But if I end up getting the probability x is equal to 0 given y is 1 is equal to probability x is equal to 0, based on this, we cannot conclude they're independent, because you need to show this holds true for all possible x and y. You will need to check probability x is equal to 1 given y is equal to 1. Then you would also need to check probability x is equal to 0 given y is equal to 2, probability x is equal to 1 given y is equal to 2. So we would need to check the conditional PMF of x first given y is 1, then we would need to check the conditional PMF of x given y is equal to 2. If every single time it's equal to the marginal PMF of x for all pair x and y, then we can conclude the independent. So to prove the independent, you need to prove any one condition for all pairs x and y, but to prove they're not independent, you just need to show that any one condition is not true for a single pair x and y.